Well, welcome to our newest episode of Extreme Reloading. In this episode, we're going to be focusing on exterior ballistics for the Ruger precision rifle, specifically looking at trajectories. So we've already spent quite a bit of time working up the load, calculating or measuring the muzzle velocity with our Euler chronograph, and now it's time to start thinking about the trajectory and how I'm actually going to be able to enable long-range precision shooting. So I've recently learned about Hornady's new product called the 4 Degrees of Freedom Ballistic Calculator. So I visited their website and frankly I find this to be very, very interesting. There's so many advances today in bullet design and the understanding of ballistic science. So the tool itself is available at this website right here, and I'll put that website in the comments. But it looks like a daunting tool to make use of, but I'm going to encourage you to take a look at the instructions, which are here. There's a YouTube video that Hornady has made available, and they also tell you what sort of information is going to be required to run this tool, and then there is a little bit of information about each individual input that you're going to be making use of. So I've gathered all my materials and I'm ready to run some ballistics. We're going to start on this dialog working from top to bottom, left to right. I'm going to be running standard calculations, so things will be measured in inches and yards and so on and so forth. My range units are given in yards, and I want my results shown to me in true MOA. Now you know that just conversationally we say that 1 MOA is pretty much 1 inch at 100 yards, 10 inches at 1,000 yards, but that's not really true MOA. True MOA is 1.047 inch at 100 yards and so on and so forth. So this is going to calculate for us true MOA. Now, one of the bullets that I've been utilizing in my .308 Winchester Ruger precision rifle is the Hornady ELD 168 grain ELD match. So I'm going to choose this. I do not see in the list, at least not right now, I do not see the Sierra 30 caliber 168 grain tipped Match King. I see a Match King, but it's not the tipped Match King, and those two bullets actually are different. I'm going to turn on temperature sensitivity factor, and here I'm going to select my Varget powder in this case, and I'm going to tell it that my baseline temperature came from 34 degrees Fahrenheit, at which point I had chronographed 2,635 feet per second. My maximum range, I'm going to run it out to 1,000 yards with 50-yard intervals. My rifle is zeroed for 200 yards, and sight height, it's very common, very normal that we just say it's 1.5 inches, but spend a little bit of time on this, and I think what you're going to find is, especially with the Ruger precision rifle, you're not going to have your sight height at 1.5 inches. In fact, mine is 2.6 inches. That is the distance from the center line of the bore to the center line of those reticles, essentially the crosshair of those reticles. It's darn close to 2.6 inches. My shooting angle is going to be left at 0. I'm going to run with the default on this. I'm going to also use a 10 mile per hour wind. The wind angle is going to come at 90 degrees. Now this is interesting because if we look at and talk about the Bernoulli factor, we might want to run it from a 90 degree crosswind. We also might want to do a 270 degree crosswind, because those two things, especially at long range, are going to make your bullets do slightly different things. Now let's move down. Here we're looking at, here this is asking for our altitude, The altitude of the shooting range that I use is 4,845 feet above sea level at the shooting bay. My pressure, now this is important to have an uncorrected pressure, so I'm getting readings from the Kestrel handheld anemometer or weather station from one of the most recent times when I was out shooting. Temperature, I'm going to run with 60 degrees Fahrenheit. Humidity, I'm going to leave at 50. Barrel twist is 1 turn in every 10 inches. Bore diameter is indeed at 308. And this axial form factor, now the first time that you run this thing, leave it at 1.0. We can come back in the future, rerun this thing, and modify the axial form factor. This allows us to tune the standard drag coefficient against what we're actually seeing. So we can measure some residuals. This thing, the 4 degrees of freedom ballistic calculator, might estimate a 3-inch drop at 300 yards or a 4-inch drop at 300 yards. But what we might see is that we're actually dropping 3.75 inches, so there's a 1/4 inch residual. Now we can play with this a little bit. We can tune this a little bit so that this ballistic calculator matches what we're actually seeing out to a given range that we feel comfortable we're really shooting very, very accurately. And it's not so much us making a mistake or something like that, the way we squeeze the trigger, so on and so forth. And we should have some very, very good ballistic trajectories to work off of. I'm going to go ahead and turn on what's called Earth-based effects. This will account for what's called the Coriolis effect. So my azimuth of fire at the shooting range that I go to is 76.53 degrees. That's the bearing, or rather the azimuth, I should say. And the latitude, which is important, longitude's not the important thing here for Coriolis effect. It's the latitude that is. I'll get rid of this 0. Now what I want to see on my display fields is range, total come up, total windage. I want to see a no wind trajectory as well. I want to see my velocities, time of flight, and leave the gyroscopic stability turned on. Let's calculate. Now, how does this look? With that bullet, take a look here. We can maintain the speed of sound all the way out to 1,000 yards. But what's also very important is that we look at what's called the Transonic Region. That is the speed of sound, 1,100 feet per second at this elevation, plus or minus 20%. So that means that I will start going transonic right around here, 900 yards. And once we get into the transonic region, I typically don't like to shoot into or try to go through the transonic region, just because some really unpredictable stuff happens to your bullet and its flight path. Now, the results that we get from the Hornady 4 degrees of freedom ballistic calculator on screen are very good, but I think the even more useful output is available from the download of that Excel spreadsheet. Let's take a look. So here's the Excel spreadsheet as output for my 30 caliber 168 grain ELD match bullet out to 1,000 yards with 50-yard increments. The first thing I like to do with this is kind of clean this up just a little bit. Notice that we're carrying a lot of decimals, and in reality we can't click to a thousandth or 10,000th of a decimal, so there's really no reason to even display those things. So what I'm going to do is adjust this in Excel, and I'm going to show 1, maybe 2 decimal places. 2 might be useful just to give us a feel for what's really going on. The next thing that I'm going to do is I'm going to delete the milliradians or I could simply collapse those fields like that. The reason I'm doing that is because I'm working on my rifle in MOA. And that just makes this just a little bit easier to comprehend. Now let's go over things just a little bit. Notice that we see my muzzle velocity displayed here is 2,639 feet per second. Yet I typed in 2,635. But I also turned on temperature compensation. So while I selected the Varget powder, gave it 2,635 feet per second, chronographed at the muzzle at 34 degrees Fahrenheit, I also told the 4 degrees of freedom calculator that I was firing at a different temperature. And so it compensated for or adjusted for that change in temperature. Now, Varget is an extreme powder. It's a temperature compensated powder, but that doesn't mean that it flatlines across all temperatures. It means that the variability in muzzle velocity is minimal or minimized due to temperature differences. So what I should be expecting then at this temperature is 2,639 feet per second. Now as we look down my velocities all the way out to 1,000 yards, I'm seeing that I end up at 1,103 feet per second estimated. Now that might be good news, might look like very, very good news, because if you kind of know some things about the speed of sound, we know that the speed of sound is roughly 1,100 feet per second. What we're seeing is that at the elevation that I'm shooting at, my speed of sound is 1,097 feet per second. Okay, it's roughly 1,100 feet per second. So that means that my velocity at 1,000 yards is good. However, let's look at this. Let's consider the transonic region. The transonic region is pretty much accepted to be at Mach, speed of sound, 1.2 through 0.8. So there's this turbulence effect that happens in that transonic region. And some bullets are more or less susceptible to that turbulence encountered throughout the transonic region. The Sierra Match King, while it's an excellent bullet, is kind of known by a lot of long-range shooters and bench rest shooters to be susceptible to that turbulence in the transonic region. In reality, what I've found is you've got to pretty much assume that all bullets are going to be susceptible to the turbulence in the transonic region. And so what we're really looking at is that I can reliably use this rifle out to the point where it enters the transonic region. So we're going to back this out to 1,320, or roughly 1,300 feet per second. So that then puts me somewhere between 800 and 850 yards. Maybe it's 825 yards where we enter into that transonic region. I'm just going to highlight that. Let's say that I can now effectively shoot out to 800 yards and not worry at all about that transonic region. Now my trajectory in inches will drop all the way out to that point 190 inches. It'll drop. To correct for that, I can spin up, do a come up in MOA of roughly 22, and I would do 22 3/4 since I have quarter MOA clicks. Interesting, if we look at this, my Schmidt-Bender scope, I can spin that thing way beyond 35 MOA. Okay, so that really takes care of our elevation. That's maybe the easy part. And if you're shooting under calm conditions, that's really all you need to take care of. But we rarely get the chance to shoot over calm conditions. We have to be very, very picky if we're shooting over calm conditions only. So we got to learn to deal with wind. And the 4 degrees of freedom calculator shows us quite a bit of information about how our bullet is going to act in the face of wind. So if you recall, we had input a 10 mile per hour crosswind crossing at 90 degrees. That 90 degrees means that the wind is coming from the right, blowing toward our bullet, which means that it's then going to push our bullet to the left. And what we're going to get at 800 yards then is a push of almost 60 inches, 59.25 inches, which accounts for a wind drift in MOA of 7 MOA. Now, isn't this interesting that our spin drift is a negative 7? Spin drift is the effect of the bullet's spin, the rifling that is imparted on that bullet. Nearly all rifles use a right-hand twist. So then if we imagine that the bullet is leaving from the shooter's position to the target, and we're looking at it in that way, the right-hand twist means that the bullet is spinning in a clockwise orientation. That then causes a high pressure and a low pressure front point on that bullet. And the bullet will then move toward the low pressure point. In this case then, because of a right-hand spin, we're going to see the bullet moving to the right. The wind was pushing it to the left. Spin drift is pushing it to the right. So to correctly compensate for observed wind conditions, 10 miles per hour, and spin drift, we can do a little bit of work. Okay, so I've inserted a brand new column, and I'm going to enter correction. I'll just call this field correction. And it's going to be expressed in MOA, minutes of angle. And I'm going to write a quick expression here. To enter the expression mode, I'm going to simply type a equal sign. And I'm going to take, I'm only looking at the MOA here, I'm going to take wind drift in MOA plus spin drift in MOA. My correction at the muzzle, of course, is 0. Do a speed fill here. The total correction that I need has then changed. And out to 800 yards, instead of correcting 7 MOA, or 28 clicks, I would do 6.25 MOA. That would be 25 clicks. 4 clicks per MOA, that's 24, and another quarter MOA, that's 1 more click, so 25 clicks. Now let's look at this gyro field. This is gyroscopic stabilization, or sometimes called that. Okay, shorthanded. Now the value we like to see here is 1.5 or higher. 1.50 or higher. And this is really a result of the rifling, the rate of rifling, so 1 in 10 in this case, the length of the bullet, the elevation that we're shooting at, and really the air density, the muzzle velocity, and so on and so forth. Remember that long bullets are harder to stabilize gyroscopically. Shorter bullets, fatter bullets tend to be a little bit easier to stabilize. There is a possibility of overspinning these things, but we're not going to worry about that. We don't have to worry about this. So here is our gyroscopic stability point, 1.5, and everything above that we can consider is stable. And as we move downrange, we can expect our gyroscopic stability to increase. And that's exactly what we're seeing. Okay, lastly, let's look at this vertical wind jump. Now what this is an effect on the bullet pretty much as it leaves the muzzle and it strikes a crosswind. Now the effect, as you can see, is pretty much constant as far as MOA is concerned, although the actual size, the empirical size of the vertical wind jump does increase as you would expect over ranges. But an interesting thing to consider or understand about vertical wind jump is that it is exacerbated with bullets that are spinning more rapidly or bullets that are exiting the muzzle of a rifle with faster rate of twist. So all in all, the Hornady 4 degrees of freedom calculator is very, very useful, looks very useful. Now what I'm also interested in looking at is how it compares to other ballistic software, the stuff I've been using made available from Tiberisaurus Rex, and of course to see how well it translates to field and real observations. Well, how do we know if this calculation is correct? Once again, I have the Hornady 4 degrees of freedom calculations here opened up in Excel, and I've color-coded some things and kind of formatted it to look just a certain way. Well, I think one of the easiest ways to help determine how good, how accurate the Hornady 4 degrees of freedom calculator is simply to compare it to other existing calculators. For instance, let's look at Applied Ballistics. You know, it's a very well-respected ballistics calculator. And in all of these cases, we're calculating, or I'm calculating, the trajectory for the .308 Winchester Ruger precision rifle with the same 20-inch barrel, the same 168 grain Hornady ELD match bullet with a muzzle velocity of 2,639 feet per second that was chronographed at 34 degrees Fahrenheit using Varget powder, 44 grains. And if we look at the 1,000-yard calculations, we're seeing some differences in velocity, as well as obviously some differences in elevation adjustments, as well as some differences in the windage. Now, what you'll notice is this is talking about a negative windage, and these are all expressed in MOA. This is showing a positive. Now, that doesn't mean that they're different by 16 MOA. Rather, this is the correction. So we need to adjust 8.82 MOA to the right, while this is telling us what the wind is doing. It's pushing our bullet 8 inches to the left. So they're really pretty much telling us the same thing. Another well-respected calculator that I've used quite a bit is the one available through Tiberisaurus Rex program. And this one again, if we look at the 1,000-yard calculation, we're seeing very similar calculations, very little difference, and the windage is a little bit different in this case. Another very, very well-respected calculator is the one made available by Lapua, and it's called Lapua's 6 degrees of freedom. It's an app for your iPhone, Android like I have. Now, the Lapua 6 degrees of freedom, again, comparing the 1,000-yard calculations, and I'm using the 1,000-yard calculations because these things are going to show the most extreme differences. We're going to see smaller differences, almost negligible differences, you know, at 200 and 300 yards. But if we look at the 1,000-yard calculation, that's where we're going to see these different calculators really start to spread apart if they indeed are calculating things in a different way. So here we have MOA once again. That's different. Okay, one's saying, Hornady is saying 35, and in fact pretty much everything is saying 35, 35 and a half. Lapua's is coming in at 33 and a half. Lapua's is also kind of interesting because they just tell you the number of clicks that you need to deal with, and that's kind of nice also. Correction for wind over here is the 8.5 MOA. Very similar kind of across the board. Now what do we call similar and what do we call different? So what I have here is I have calculated the differences. Here is the difference between Hornady's application and applied ballistics, Hornady versus Rex, the Tiberisaurus Rex project, and then Hornady versus Lapua. And I simply calculated that difference in all of their calculations, in all cases. And then what I did is I highlighted here in this kind of orange color all of the differences that amount to literally a difference in the click. Will I click one more or one less with Hornady versus applied ballistics, or 2 or 3, whatever the number of clicks? If it's not even a click, I'm going to call it an insignificant difference. So we're seeing in almost all cases Hornady and applied ballistics is agreeing perfectly. Very, very, very well. Hornady versus Rex, you know, a lot of them are about a click different. And the major difference really between Hornady's 4 degrees of freedom and the Rex project is in the wind. And so I wonder which one really is more accurate, realistic, when we're dealing with wind. Now it's going to be a very, very difficult one to test though, because we'd have to have a consistent wind out to a very long distance, even a nice consistent wind out to 250. Maybe we could pull that off. I don't know. Winds are so variable and they change over distance. This would be a very, very difficult one to determine which one is correct. And then we have some kind of odd results with disagreement, then agreement, disagreement, and then agreement again when we compare Hornady to the Lapua 6 degrees of freedom. The other thing I wanted to point out again is let's not forget that transonic range. So we're going to be going transonic at about 920, 930 yards. So then again, we can kind of ignore these places that have differences, not because they have differences, but because we're not going to shoot that anyway, because we're transonic. That means that the Hornady and applied ballistics calculators are literally identical. Here we have, a click. Here we still have just one click. I wouldn't move it more than one click here. It's only a 0.34, so we're only one click difference. Again, these are one click differences. But here, the Lapua 6 degrees of freedom, on many, many cases, we are at 2 clicks, 4 clicks, 3 clicks. So I'm really not going to put too much faith in the Lapua 6 degrees of freedom app. I know a lot of folks think the world of it, but it's so different than everything else that we're seeing, and I've not had problems with the Rex project. I've had some really nice results from that one. I have used applied ballistics before. I've used Rex's project a little bit more. I'm going to look much more closely at Hornady in the field. But there we have it. There's really not that much difference. It's going to be kind of pick your favorite, whichever one seems to work nice for you, whichever one has a good interface that works well for you. And these things are going to get you, in the ballpark, really, really close in the ballpark. The rest is going to be up to you to hit that target, to hit that bullseye. It's going to be your hold, your rifle cant, your breathing, your trigger squeeze. It's going to be the rounds that you're using. How consistent are they? Are they really all starting off at 2,639 feet per second? How much variability do you have there? Because out to 1,000 yards, things are going to start moving. If one's going 2,600 feet per second and another one's going 2,650 feet per second. Well, so I hope you've enjoyed this segment of Extreme Reloading. Thanks for watching.